that sounds good.
Okay, so welcome everyone to statistics seminar. So today we have Iain Carmichael from our department. Iain is currently a postdoc fellow working with Stella, and Iain get his PhD in the UNC working with Steve Maron and Shankar Bahamid. And Iain working on a lot of problems about like computational methodology for complex data set, including like network data, imaging data, and like multi-view data. And today he's going to talk about very exciting work about sparsity structure estimation for multi-view mixture models. And let's welcome Iain. And by the way, if you have any questions, please make good use of the Q&A sections or raise your hand. Okay.
Thank you, Yanchi and Christine, for setting this up. So as Yanchi mentioned, I'm going to be talking about mixture models in the context of multi-view data. So, but by the way, is the Zoom thing at the top covering the title, Yanchi?
No, it's not covering title.
Oh, okay, sorry, on my screen it is. This project was motivated by the applications I worked on in grad school on integrating breast cancer histology and genomics. So in cancer, there's sort of two broad approaches to studying cancer and diagnosing cancer. And so the first is histology or histopathology. And that's where a doctor extracts a piece of possibly cancerous tissue, and that tissue is then visually examined by a pathologist who makes various determinations, things like tumor grade or histological subtype. More recently, genetic-based approaches have become popular and have helped provide a more clear picture about, for example, what treatments are effective. And so this project was sort of motivated by doing exploratory analysis with these kinds of data. So for the rest of this talk, we're going to be working in what some people call the multi-view data setting. So that means a fixed set of n observations and multiple sets of variables. So for example, we might have two blocks where we have maybe 400 patients, and for each patient we have a set of clinical measurements, height, weight, blood pressure, and we have another block of genomic variables, maybe 10,000 gene expression variables. And so this settings has a number of synonyms like multi-view, multi-block, etc. And the link I pointed to at the bottom is a GitHub repository from Mike Love, who has a nice list of like recent software and methods in this area. I think that the most common algorithm or method that people are familiar with in multi-view data is canonical correlation analysis, which is a dimensionality reduction for two data blocks that says, okay, I have two data blocks or two data views, and I think there's some kind of joint signal. There's some kind of latent variable that explains the variation in both data blocks. I'm going to estimate that latent information, that joint information somehow. More recently, there's been work on clustering, and what I'm sort of broadly calling consensus clustering, which means I have two or some number of views. And I think there is sort of one set of joint clusters, and those clusters show up in kind of every view. So I'm grouping these methods together in that they kind of focus on joint information, what's shared by all of the data views. More recently, there's been a focus on partially shared information. So things like dimensionality reduction with partially shared signals, or joint and individual, or this nice paper, joint and individual clustering, where I think there's sort of sets of clusters in one view. I think there's sets of clusters that are kind of jointly show up in both, and maybe sets of clusters that are in another view. In this paper I'm highlighting because it's sort of similar in spirit to the application we're going to be talking about today. Also, sort of more recently, there's a nice paper from Lucy Gao and Daniela Witten in our department where they develop tests for associations between clusterings in multiple data views. And that paper kind of inspired this work on cluster estimation. So for the rest of so I'm going to first describe the mixture model that we're going to be thinking about in the rest of this talk. And then we're going to focus on estimating the sparsity structure of one of its parameters, the pi matrix, which plays the role of sort of the weights parameter in a simple Gaussian mixture model. And we're going to look at two different ways, two different approaches to estimating that sparsity structure. So the mixture model. The setting we're working in, we're going to assume we have a V-view data set. So and I'm going to use superscripts to correspond to views. So each xv is a d sub d super v dimensional vector, and we might concatenate them together to form x, which is a sum over dv dimensional vector. And so that's going to be our random vector, and we're going to when we get data, we're going to observe n of these random vectors. And so the main so we're going to assume that if you look at each view marginally, so just look at the first view, each view marginally follows some mixture model. It's let's just pretend it's a Gaussian mixture model, and maybe only the means vary, just for simplicity. So if you look marginally in the Vth view, we're going to say there's kV clusters, and then YV is of course going to denote the latent cluster view label. So this mixture model has been studied in a few different by a few different papers, including Danielle and Lucy's. And I think the first reference that I was able to find for this is that 2004 paper. So I just told you about the marginal distributions for these data views. Now let's construct the joint distribution for that concatenated data vector. So that joint distribution is determined from those marginal distributions and this pi matrix. So this let's assume we have I guess it's a multi-array describing the joint distribution of the latent view cluster labels. And pi is defined like this. So putting pi together with the marginal view distributions completely describes the distribution. And I'll show a picture of this in a sec that I think will make this a little more intuitive, but just to kind of be concrete, the concatenated data vector follows a mixture model that if you just look at the concatenated data vector, that has at most the product of k number of components. And its PDF, of course, looks like that, which is mild generalization of just a standard single view mixture model. But I think a better way to understand this model is by looking at some data examples. So here's a two-view data example where each view has one feature. In my first view, there are 5 clusters, and each, these are Gaussians with different means. In the second view, there's 3 clusters. So this is kind of the basic data model. And so I should say in this view, with this data set, the views are independent of each other. So that pi multi-array is a matrix, and that pi matrix is rank 1. So here's another example with a little bit more dependence. So here the pi matrix is not rank 1. In this case, I think there's 15 clusters if you look jointly. There's 9 clusters if you look in I guess the second view, marginally in the second view, and 10 in the first. And so this is going to be this second example is really the sort of motivating data example that the motivating scenario that we're going to be thinking about for the rest of the talk. And just to go all the way to the other extreme, here's an example where there's sort of total of the most dependence you can have between the two views, where if you look in the first view, there's 5 clusters. If you look in the second view, there's also 5 clusters. And actually the cluster 1 in the first view is exactly the same as cluster 1 in the second view. And so this third example would be kind of what those consensus clustering methods that I mentioned before would be targeting. But our focus is going to be on this middle example, where we think there's some kind of interesting dependence between the two views. Or in particular, there's some kind of joint information, but there's also some kind of individual information or view-specific information. So So now how do we fit this model? And in the basic setup, we're gonna fit it with maximum likelihood. So we're gonna minimize the given n observations, minimize the negative log likelihood, and we're gonna do that using an expectation maximization algorithm. So this is all pretty standard if you're familiar with EM for single single view mixture models. These calculations it's just a little bit of additional algebra to go through this. So EM is an iterative algorithm. We're gonna update our parameters at every step in the following way. Given our current estimates of the parameters, we're gonna construct a surrogate function. So we're gonna construct some function Q that's a function of pi and theta. And this is done using the conditional expectation of the complete data log likelihood. So again, that's totally standard for mixture models. And the Q that I wrote there is a surrogate function sort of up to some uninteresting constants. And then in the second part of the update, we're gonna minimize the surrogate function. So EM is of course a majorization minimization algorithm. And to update in that M step, the Q separates into different terms for theta. So theta was the cluster parameters. So the means for every view's cluster. Pi is again the mixture weights multi-array. And so we're gonna have separate problems for theta and pi. The problem for theta is just a weighted maximum likelihood problem. And it is pretty straightforward to solve. And at least in this case, pi has an analytic solution. So, sort of O of 1 update. And so I'm presenting this EM algorithm because the methods that we're going to present later use this algorithm up to one detail, and that's the update of the pi matrix. So in the algorithmically, and for the models I'm going to talk about later, the only thing that's different is how we update pi. So pi is the kind of, if you're interested in the dependence or between the data views, pi is kind of the interesting parameter to look like. Pi really captures the dependence between these two views. And so Lucy and Daniela had this nice paper asking, well, are the clusters in our views independent? So in the case of two views is pi a rank 1 matrix. We're going to look at, so they look at testing. We're going to look at estimating the sparsity structure of pi. So taking a little bit more of a careful look at this motivating example. So on the left, I'm showing, again, that same two-view, two-dimensional data set. And on the right is the corresponding pi. In this case, it's a matrix. And so this pi matrix has an interesting structure, which gives sort of interpretable information to the analyst. So these bottom two right clusters, we might call joint clusters. So in other words, cluster 1 in view 1 is exactly the same thing, is exactly the same as cluster 2 in view 2. So for example, in the breast cancer example that I was talking about, in the histology, maybe high grade tumors are exactly the same subtype as basal tumors in the genetics. Okay, so we might have joint clusters. We might also have these hierarchical clusters. So cluster 3 in view 2 breaks up into clusters 3, 4, and 5 in view 1. So maybe low grade tumors, that's a pathology class, can be either luminal B, HER2, or normal subtype in the genetics. We might also have blocks of clusters, so like that. And so this is kind of the structure that we think might be present in our data. And our goal is now to recover this kind of structure somehow from data. So the natural approach is of course through penalized likelihood. Well, I should say there's two approaches that you might try, and the first is the straw man, the naive enumeration approach. So conceivably we could enumerate over all possible sparsity structures of pi. for each structure, fit an EM algorithm, and then pick the pick the structure that gave the best BIC, for example. Of course, that leads to an exponential search space, and is probably computationally infeasible in most cases. So we're then going to turn to a sparsity-inducing penalty. So we're going to consider the following penalized maximum likelihood problem, where we're maximizing the likelihood. I've added on some penalty term, and that we're penalizing the entries of the pi matrix, each entry of the pi matrix, or multi-array, sorry. And I've also written out the constraints. So the blue part is the only thing that's new to from the sort of basic setup. But I have written out the constraints here to emphasize that the pi matrix, the entries are positive and sum to 1. And so that's worth paying attention to, because of course the most natural penalty to turn to would be the lasso penalty. However, in this case, the lasso is constrained to be constant, so we're not really going to get anywhere if we just throw a lasso penalty on. Not to worry, there's plenty of other sparsity-inducing penalties, things like SCAD, for example, but those are concave. And that concavity raises some computational challenges with the EM algorithm. So first well, if we have a concave term, previously our M step had an analytic solution. That's because it was the solution to a nice convex problem. And the problem that the M step solves is written here. And without the penalty, you can just set lambda to 0 and you would get the original M step. And it's not too hard to see this has an analytic solution. But with that P term, especially if it's concave, then that means we might have to use some kind of iterative algorithm. So in other words, that means the M step would be much slower. That's a little bit bad, but maybe not terrible. But even worse, if our goal is to get sparsity, there's a log barrier term in the M step, meaning that we can never get an exact 0. So that log term that I've highlighted in blue means the solution to this problem can never have a 0 in any of the entries of pi. I think someone's asking a question. So there's a question. So I'm clicking on the Q&A and it's not popping up. Yanchi, can you see the question, the Q&A?
Yes, I think I can just read it for you. So the question is, would you mind defining the sparsity for pi here?
Defining the sparsity for pi. So, so in our, right, just going back to the model. So pi is the cluster weights parameter. So pi says what's the probability that an observation is in cluster 1 in V1 and cluster 2 in V2, etc. And so pi being sparse means that so say the pi 1, 1 is 0. That means you can't have an observation that's in cluster 1 in V1 and cluster 1 in V2. I guess I can't see if that answered your question, but hopefully that answered your question. So pi having 0 terms, here's a sparse here. So on the right, if that's an example of pi, this entry 1, 2 over here means you can't have an observation in V1 and in cluster 1 in V1 and also in cluster 2 in V2. Okay, so as we were saying, we're going to estimate this. So we think pi might be sparse. We're going to try to estimate the sparsity structure through a penalized likelihood formulation. We're going to use an EM algorithm to try to fit that model. And there's some computational challenges with this EM algorithm. So in particular, we have this log barrier term, like I said before, means that our EM algorithm can never actually give an exact 0. due to the log barrier term. So we'll come back to that issue. We're going to pick the log of delta plus x penalty function, and so this was it's shown up a few places in the literature, but there's this nice paper by Huang et al. That provides some consistency results for using this penalty in the context of a mixture model. So if you put this penalty on the weights coefficient in just a standard, say, Gaussian mixture model, you get some nice consistency results. So we have some theoretical reasons to think this might be a good idea. We of course can't use lasso due to the sum constraint, and it turns out there's some computational advantages to using this log term. So in particular, there's a soft thresholding approximation of the M step that's been proposed as a heuristic in the literature, and I'll talk about that. So right here I've written out the M step that you get if you use that log of delta penalty. And so it's minimize, sum of AK are just some constants that come from the expectation step of log pi k plus penalty on the sum of the log of delta plus pi k's, subject to our probability constraints. So this is a non-convex problem. The first term is convex, the second term is concave. So we shouldn't, expect a nice solution. But it turns out, and finding the global minimizer of this, I don't claim is easy, but it turns out there's a nice soft thresholding approximation. So let's let S lambda be the normalized soft thresholding operation. So S lambda takes a vector A and it spits out another vector. It's going to apply the soft thresholding operation to every entry of A. And so that's written right here, A minus lambda, maximum with 0. So the soft thresholding operation will set terms to 0 when lambda is bigger than, say, AK. And then we're just going to normalize the result. So it sums to 1. So so the vector that the normalized soft thresholding operator spits out is normalized to sum to 1. And this has been proposed as an approximation for the M step. And it has a couple advantages. So first of all, it avoids slow computation of an iterative algorithm. It's an O of 1 step, so it's very fast. And it also gives exact zeros, where we couldn't have gotten exact zeros due to the log barrier before. And so this has been proposed as an approximation of this M step. But I hadn't seen it really proved anywhere. You can kind of argue heuristically this seems like a reasonable thing to do, but it turns out you actually can prove that this is a rigorous approximation in some sense, and so that comes from the following theorem. Let's consider the optimization problem that's written there, and that's the same optimization problem that comes from the M step. For a fixed value of delta, let's let x delta be a global minimizer of this problem. And I use the in notation because this is a non-convex problem and it's possible we have more than one. But let's let x delta be any global minimizer for a fixed delta. Well, it turns out that if you send delta to 0 and look at x delta converges to the soft thresholding operation. And so to prove this, you can prove this by looking at the KKT conditions and doing some analysis with that. So what this theorem says is the solution of the log penalized problem. I don't really know what it is, but if delta is pretty small, then we can approximate it using soft thresholding. Right. So okay. So we're now armed with an EM algorithm, our sparsity-inducing log penalty, and our EM algorithm. Where the only difference between this EM and the EM for the base model was to replace the M step with the soft thresholding operation. Another thing to note is delta kind of goes away at this case because it doesn't show up in the algorithm. So the only place delta really shows up is when you're monitoring convergence for the EM algorithm. So delta is sort of no longer an important modeling parameter with in this model. Really, the only tuning parameter for this model is lambda, which controls the sparsity of the solution. So to do models, so we're going to fit this model for a bunch of different values of lambda. And we're going to do model selection using a modified BIC criterion. And so this is based on that Huang paper. And all we've really done is it's the BIC we all know and love. And but to count the number of parameters for the pi matrix, we simply use the support of this pi matrix for the given value of lambda. And so Huang proves that this estimator, at least in the single view case, has some nice consistency properties. And so this work is still in progress, but I'll show just a quick simulation to show that it is working. So in this simulation, we're going to have two data views, a 5-dimensional, and actually that should say a 10-dimensional view. And in the first data view, there's going to be 5 clusters. In the second view, there's going to be 8 clusters. Each view is going to follow a Gaussian mixture model with a spherical covariance parameter. And some sigma controlling how hard the problem is. And we're going to assume that pi is sparse, so about 40% of the entries are set to 0. And we're going to compare the log penalized mixture model with the Gaussian mixture model, with fitting a Gaussian mixture model on the concatenated data. And so we're going to evaluate the simulation in 2 different ways. So first, we're going to evaluate, well, how well does it predict the cluster labels after fitting the model? So in this data set, the x-axis is the number of estimated components. The red curves correspond to a Gaussian mixture model on the concatenated data views. And on the y, the blue corresponds to the multi-view mixture model with the log penalty. Fit for a bunch of different lambda values, and then the y-axis is the adjusted rand index. So by that I mean, for after fitting a model, I'm going to show it a bunch of test data points whose cluster labels I know. I'm going to ask the model to predict what it thinks the cluster labels are, and the adjusted rand index is a way of measuring how well 2 clustering sort of concord with each other. And sort of the upshot of this is the log penalized multi-view mixture model, it does significantly better than the concatenated Gaussian mixture model. And the stars show the performance at the BIC estimated model for the log penalized model. And so these stars kind of going up. Oh, and sorry, the curves showed these models fit on different numbers of training samples. So all the way from 100 training samples to 1600. And so these stars going up, so, tell you what you would want, which is, as you increase the number of samples, the BIC estimated model gets better and better. The second way we're going to evaluate this is, well, let's try to measure how well did we estimate the pi matrix. So the estimated pi matrix is a little bit difficult to evaluate because of course in a mixture model the cluster labels are arbitrary. So we don't really know what the sort of correct permutation would be, so that you could actually compare, the estimated pi matrix with the true pi matrix. But we're going to do something simple, which is we're going to do a greedy alignment of the estimated means to the true means. And so by that, I mean, I'm going to look in every view, find the closest pair of means, find the closest pair of estimated and true means, align those, find the second closest, etc. Do that for every view, and that's going to give me sort of an aligned pi matrix. And then I'm just going to look at a measure of distance. So I think in this case, it's the mean absolute error between the true pi matrix and this greedily aligned pi matrix. And what this plot shows you is, when the number of samples increases, we get more and more accurate. And again, the BIC estimated model gets better and better with more training data. So that's it for now for the general sparsity case. Now we're going to think a little bit more about structured sparsity. So I think the most interesting form of sparsity is this block diagonal structure, right, that we talked about before. So these bottom two right clusters, we might say are joint clusters. So cluster 1 and B1 is cluster 2 and B2, and that's that might be interesting for the practitioner, or these hierarchical clusters or blocks of clusters. So I think that the next most interesting thing to do instead of just general sparsity is block diagonal sparsity. So of course, like I mentioned, the cluster ordering is arbitrary. So we don't really want to just talk about block diagonal matrices. We need some notion of a matrix that's block diagonal up to permutations. So the matrix on the left is kind of you can see the block diagonal structure. The matrix on the right, all I've done is permute the rows and columns. We want to consider both of those block diagonal in some sense. And so how do we do that? And I'll come back to that question in a minute. So to be a little bit more concrete, we're just going to talk about the two-view case for now, although everything I'm going to say for the block diagonal setting generalizes to the more than two-view case. But let's talk about the two-view case. So we have some matrix pi in our K1 by K2, and we want to consider the following constrained maximum likelihood problem. So maximize the likelihood subject to the constraint that pi is block diagonal with B blocks up to permutations, which again, I'm going to define in a second. So this is the problem we're going to be interested in. And then we have this tuning parameter B, which controls the number of blocks. So how do we solve this problem? Let's abstract out the mixture model setting for a few minutes, and let's just think about optimization in general with block diagonal constraints. So let's consider the problem where we're trying to minimize some objective function f of some matrix parameter x. X is r by c, some number of rows by some number of columns, and x is constrained to be block diagonal with b blocks up to permutations, which again I'll define in a second more precisely. So there's there have been a few different methods to try to estimate things like this. Probably the most popular method uses the unnormalized Laplacian in a smart way. And I'll explain that method going forward. But just to be upfront, when I tried to adapt these sort of existing unnormalized Laplacian methods, I found that it just really didn't work for reasons that I can explain. And to get it to work, you kind of have to make stronger, maybe stronger than you would want, modeling assumptions. And without those, you really just get unsatisfactory sort of local minimizers of a different problem. But I'll explain what I mean by that in a second. So let's say we have a fixed matrix. What does it mean for matrix to be block diagonal? That's sort of intuitive, but there's just a couple of conventions we need to take care of. So we're going to use the conventions that in a fixed matrix, a block must be non-empty. So it must have some terms that are not zero, and anything that can be a block is a block. So if we look at this example matrix here, someone might argue this matrix either has 1 block, 2 blocks, or 3 blocks. And based on our conventions, we're going to say, no, this matrix has 2 blocks. Okay. So now block diagonal up to permutation, and I promise in a minute there's a more interpretable definition coming up, but the number of blocks of a matrix up to permutations is, well, let's look over all possible permutations of the rows and columns of this matrix. Some of those permutations are going to give block diagonal matrices themselves, and let's find the permutation that gives us the most possible blocks. So when we say the number of blocks up to permutations, that's what we mean. But now for a little bit more interpretable definition, we're going to take a network's perspective on this matrix. So we have some matrix X. Oh, and I guess I should emphasize that our matrix X is always constrained to be positive. So we have some matrix X, R columns, or R rows, C columns. Now let's think of a bipartite graph on R plus C nodes, whose vertex sets are the rows, and whose other vertex set is the columns of X. And then the edges of this graph are given by the entries of X. So on the bottom left, there's an example matrix. It's 3 rows and 5 columns. And on the right, I've shown the corresponding bipartite graph. So this graph is nice because the connected components of this graph with at least, that should say, with at least 2 vertices, I'm sorry. With the connected components of this graph with at least 2 vertices count the number of blocks in this matrix. So this top left block over here is, of course, this connected component. This block over here is, of course, this connected component. And we have this column of zeros here. And that's going to correspond, of course, to this isolated vertex. So this matrix has 2 blocks up to permutations. And the graph on the right has 2 connected components that have at least 2 vertices. So we ignore isolated vertices. Okay, so now we're in the world of networks. I just need to make a couple network definitions. So let's say we have some undirected graph G, no self loops, and let's say G has positively weighted edges, and it has some adjacent matrix A, A is symmetric, has zeros on the rows. The unnormalized Laplacian is given by this formula. So take the row sums, or the degrees of every node, put those into a vector, put that vector on the diagonal of some matrix, that's this first term, and then subtract off the adjacency matrix. The unnormalized Laplacian, this is a quantity many people are probably familiar with. It's used in spectral clustering, for example. And then, of course, we have the well-known fact that there's a one-to-one correspondence between the connected components of the graph and the 0 eigenvalues of this unnormalized Laplacian. Turns out we're going to actually need the symmetric normalized Laplacian. And that's defined by take the unnormalized Laplacian and hit it with the diagonal matrices who are the square roots of the degrees. There's an important convention with the symmetric Laplacian, and that's what happens when you have a degree 0 node. And so we're going to follow the convention that when there's a degree 0 node, the diagonal element of the symmetric Laplacian is 1. This corresponds to using the Moore-Penrose generalized inverse in this inverse right here. And I should say this convention is not always followed. And so I'm going to give a proposition later on that will look a little bit different than if you look at, for example, this famous von Luxemburg spectral clustering tutorial. So we have the unnormalized Laplacian and the symmetric Laplacian. Okay. So now here's the important result connecting block diagonal matrices to the Laplacians. And so let's say we have some matrix X. It has B blocks up to permutations, and it has say some number of 0 rows, 0, and some number of 0 columns. As I mentioned before, that corresponding bipartite graph has B connected components with at least 2 vertices and some number of isolated vertices. The important result is 3, and that's the symmetric Laplacian of that bipartite graph. So ABP just means the adjacency matrix of that bipartite graph that I mentioned before, whose vertex sets are the rows and columns of X. The symmetric Laplacian of this matrix has exactly B eigenvalues equal to 0. So in other words, the symmetric Laplacian, the 0 eigenvalues of the symmetric Laplacian count the connecting components only with at least 2 vertices. It ignores isolated vertices. which in turn counts the blocks of a block diagonal matrix up to permutations. The reason we are going to end up using the symmetric Laplacian and not the unnormalized Laplacian is point 4, which is the unnormalized Laplacian doesn't distinguish between blocks and rows of zeros and columns of zeros. And I should say this proposition sort of generalizes fairly naturally to the case of multi-arrays. So you can define a notion of block diagonal multi-arrays. And basically exactly this proposition, if you define the sort of corresponding graph properly, exactly this proposition generalizes to the multi-array setting. Okay, so returning to our optimization problem, the original problem we're interested is minimize some function f over x, where x is constrained to be block diagonal with at least b blocks up to permutations. And it turns out that's equivalent to a spectral characterization. So we can turn the first problem, we can turn the sort of combinatorial constraint into a linear algebra constraint. So in particular, we're going to constrain the smallest b eigenvalues of the symmetric Laplacian to 0. Okay, so now we're in the world of continuous optimization. So now going from this eigenvalue constraint, how do we actually solve that? How do we actually optimize over that? Well, we're going to use penalty function. So for some sufficiently large value of alpha, so alpha is, I guess I would call it like an optimization tuning parameter. It's not a parameter of a model. It's just you need to set this large enough. So for some sufficiently large value of alpha, I'm going to penalize the function f with the sum of the smallest b eigenvalues of the symmetric Laplacian. And so that subscript with the parentheses means we're ordering things from smallest to largest. So penalize the smallest b eigenvalues of the symmetric Laplacian. It's going to turn out for some of our theoretical guarantees, we're going to need to add this additional constraint saying that the degrees have to be lower bounded by some positive constant. It's actually not important, it's seemingly in practice, and you can kind of assume it away in practice. But like I mentioned, for some of the theoretical results, we will need that eta. But I'm going to ignore that eta for the rest of the talk because it doesn't, because in practice, like I said, you can ignore it. Okay, so now we have our eigenvalue penalized problem. And I should say this problem is a little bit tricky because the symmetric Laplacian has some nonlinear terms in it. So remember, the symmetric Laplacian has those square roots of the degrees. So that makes it a little bit difficult to optimize with. I think there's another question, but I can't see it. Yenshi, do you mind reading the question if there's one?
Oh no, actually, I just that's a reminder. Just
oh
yeah, 10 minutes left. Just
got it. Thank you. Okay, so let's and so the way we're going to do that is with a mild generalization of the famous Fan's theorem. So Fan's theorem says I have some symmetric matrix A, and the sum of the smallest eigenvalues is equal to the minimum of some optimization problem. And this optimization problem is minimize this quantity right here over some matrix V, subject to some orthogonality constraints. So this is called the extremal representation of the smallest k eigenvalues. It turns out it's not too hard to generalize this to generalize eigenvalues, but I'm going to write it in the following form. Let's say A and B are symmetric matrices. Let's assume B is positive definite. Then the smallest k eigenvalues of this matrix right here, so take A and hit it with the inverse roots of B on either side, also has a nice extremal representation. When all I've changed from the previous representation is I've added B to the orthogonality constraint. Okay, so it's not too hard to show that. Now how does this help us with our original optimization problem? Well, it means we can replace the sum of the smallest b eigenvalues of the symmetric Laplacian with these terms that are going to turn out to be linear in X. So putting this all together, our previous eigenvalue penalized problem is equivalent to this problem right here, where I've replaced the eigenvalue penalty in the objective function that was there before with this extremal term here, and I've added a constraint. So this is the problem that we're sort of operationally going to solve. And this problem is nice for two reasons. We're gonna use alternating algorithms to solve this problem. We're gonna alternate between updating X and updating V. And so if X is fixed, a global minimizer in V is obtained through an eigendecomposition. So not too hard. Now, if V is fixed, we have to solve a linearly perturbed subproblem. So I've highlighted the subproblem in X or fixed V at the bottom. All of the terms highlighted in blue are constants. Oh, sorry, that X is not a constant. So C and M and D and little d are just constants in V whose values aren't important for now. But what's important to note is these are just linear terms. So we've made so if you can optimize F. And you can optimize F with these additional linear terms, then you're good to go with alternating algorithms. So that's kind of a sketch of how we solve this. So now let's come back to the multi-view mixture model setting. So again, the problem we would like to solve is do maximum likelihood estimation under these block diagonal constraints that we've placed on pi. For reasons kind of similar to the zero issues in the M step with the log penalized term, getting exact zeros with EM raises issues. So we're gonna decompose pi into the sum of some small term epsilon, and then some matrix D, where D is block diagonal, and we're gonna impose the block diagonal constraints on D. And so we're actually going to solve just the slightly different problem where maximum likelihood estimation and D is going to play the role of pi, and we're going to constrain D to be block diagonal. And it turns out, well, we can use the original EM algorithm just with a slightly different M step. So here's, I guess, one loop of that EM algorithm. So we're going to construct the surrogate function given our current parameter estimates. It's exactly the same as before. We're going to update V with an eigendecomposition. We're going to update theta with by solving a bunch of weighted maximum likelihood problems. Again, the same as before. And then we're going to update, sorry, that should say D. We're going to update D by solving the following convex problem. And it's just these log objective functions or negative log objective functions. So that's convex, add a linear term convex, and then linear constraints. And so this problem is pretty straightforward to solve with, for example, interior point methods. And I've been using like the convex optimization or CVX package, CVX pi package in Python to solve it. So this algorithm that I'm describing is essentially what's known as block successive upper bound minimization, which is a mild generalization of alternating algorithms that allow you to use surrogate functions or update surrogate functions. And so I'm still working a little bit on I cited this BSUM paper, and our setting is just a little bit different because we have this sort of added non-convexity from the coupled constraints between D and V. And so I'm still in the middle of proving convergence, but it should work reasonably well because just at least at minimum, the objective function, for example, is guaranteed to decrease at every step. So how do we do in simulations? Well, on the left, I'm showing a ground truth pi matrix our data. I think in this case, it's just Gaussian mixture models, 2 views, 10 features in each view. And I think this was probably 1,600 samples. And on the right, we get the estimated pi matrix. So it's not perfect. There's a little, the non-zero entries of pi are all the same in the ground truth, and there's a little bit of heterogeneity there in the estimated pi. And of course, this estimated pi matrix that I'm showing on the right, we've permuted it to reveal the block diagonal structure. Just to show another example where it isn't perfect. On the left is the pi matrix that I was talking about as the sort of motivating example, and on the right is the estimated pi matrix. And unfortunately, it didn't. If you stare carefully at this, you'll see it gets almost everything right, but it puts one of these joint clusters. It moves one of the clusters from this 3 cluster block here in with the joint cluster. So it's not perfect, but it does pretty well in general. And we I'm still working on some simulation results, but so far it does, it's definitely working much better than the concatenated, than Gaussian mixture models and the concatenated data views. Of course, those don't actually give you an estimate of this block structure of pi. And I think I'll stop there. So yeah, so in summary, we look at this multi-view mixture model where the dependence between the views is captured by this pi matrix or pi multi-array parameter. The structure of that pi parameter, the sparsity structure of that pi parameter, tells you about how information is shared between these different data views. So do you have joint clusters? Do you have clusters that are kind of hierarchical, etc.? So we developed 2 approaches to estimating the sparsity structure, and then deal with some of the computational issues that come up when trying to fit those models. So the first is estimate sort of an arbitrary sparsity structure using this log penalty. And the second approach is using these block diagonal constraints. And so there is and will be publicly available a Python package for multi-view mixture modeling that fits the basic model, and of course all these models that I've been talking about that will hopefully soon be available on my GitHub and on PyPy. And yeah, so stop there. I guess right in the Q&A if you have any questions.
Thanks, Ian. And any questions from the participants? I think actually I myself have a question. It's a very interesting talk. So I'm just curious that can you I was just thinking that it seems to me that if I just say instead of using the penalized like a joint modeling, I can also marginally for each view I run a Gaussian mixture model, right? So view 1 I get some partition of the class, and view 2 I also run a Gaussian mixture model. I also get a few clusters, and then I can construct something like a confusion matrix. I think that's going to be some basically an estimate of your pi. And then suppose I come up with some rules of thresholding because I kind of see that if the true is really a sparse structure, then when I compute this confusion matrix is going to have a lot of elements that are close to 0. So I don't know if this why don't you do there might be some problem with this marginal modeling compared to, I think in your method it's more like a jointly model versus this kind of marginal modeling idea.
Yeah, I mean, I wouldn't, I'm sorry, before I answer the question, I need to thank Danielle Witten also for very helpful feedback on this project. So to your question, yeah, I mean, I wouldn't really say there's anything wrong with that approach, but I mean, well, okay, so I think that approach is a reasonable thing to do, but I guess the one issue with that approach is you're sort of, there is a lot of shared, or there can be a lot of shared information between these views. So for example, in the case, say your views are independent, I think the approach you described, well, I guess if they're independent, they couldn't have a block structure. If there's not too much dependence between the 2 views, I think more simple things like that probably will work well. But if there's a lot of dependence between the 2 views, or maybe one view is maybe there's dependence between the two views, and one view is a lot noisier than the other, or something like that. Or your signal to noise ratio isn't that high, and you really want to borrow information across the two views. I think in those kinds of settings, this sort of estimate everything together will work better. But I mean, that's a good question. I should actually probably add that to the sort of baseline simulations.
Okay, thanks. Other questions from participants or like other attendees? Yeah, so maybe I can answer another question, because that's in some problem actually I was also thinking about. And I was thinking another idea is that I think you can, like the idea using marginal method has the advantage that, you know, you can plug in different methods. Like say I can do spatial clustering on each view, or I'm not limiting to the Gaussian mixture model, or I can use other kind of things and jointly. But I think the problem is that so you have mentioned that doesn't really borrow information about you. If you have really highly dependent structures, like your view, like data example, like the example you gave, like you have a lot of dependent structure, then modularly on each view, then you might not really make use of this kind of like information aggregators.
Mm-hmm.
So I was thinking that in your case that you are jointly fit models, is it possible to also say it seems to me that the idea may not just limit it to the like the mixture model. I was thinking that can you also use some other combine other clustering algorithm or methods, and also jointly using this idea, like jointly using this approach.
So I think my answer to that would be with so for example, in that block diagonal constraint setting, like if you have some notion of that pi matrix, like I can't off the top of my head tell you how you do that with like hierarchical clustering. But you can probably come up with something. If you have some notion, of that pi matrix, or just something that, measures association between clusters in different views, then you could constrain that matrix to be block diagonal. And I think that would kind of be a similar idea. Or I guess also, you could, run a lasso on that kind of matrix for just arbitrary sparsity structure. Does that answer your question?
Yeah, I think yes. That's a good point. Oh, I think there's a question in the Q&A. Okay, so there's a question about have you considered penalizing the eigenvalues of a power effect decomposition of the pi matrix?
Okay, sorry, could you penalizing the eigenvalues of what?
I think the eigenvalues of a power effect decomposition of the pi matrix.
So I'm not sure, like penalizing the eigenvalues of pi itself. Okay, so penalizing the eigenvalues of pi itself, we'll say that pi is, low rank. And that's, that's not quite the same thing as this block diagonal structure. If it's interesting to think of pi being low rank, I think you would do that. There is this part of the talk that I skipped over. I'm not 100% sure if I answered that question, but we also look at you know what? Never mind. I won't get into that. Yeah, I think I think that's probably the question they were asking. But feel free to clarify if I misunderstood your question.
Well, the idea is that, if you think about the first order decomposition, what you have is the independent case, right? Because you would be writing your pi matrix as the dot product of two vectors, that is the independent. So you consider each one of the row and column or each one of the dimensions independent. And you can extend that to a tensor of any dimension.
Right.
So as you add dimensions to this, you start to make things not independent and to move towards the kind of shapes that you have been looking at. So that would seem like a natural alternative to what you're doing, in which you say, well, if I instead penalize, so the eigenvalues. So I consider the eigenvalues in order, and I start penalizing them in order. Then you are going to have a sparse representation, and you're right. So it's a sparse in the same of the eigenvalues. It's not a sparse in the sense of having exact zeros, but it contains as the limit the case that you use as the reference, that is the independent case.
Yeah, so the penalizing the eigenvalues of pi towards 0, would encourage pi to be the clusters to be independent across the different views. I haven't thought too much about that case, but I think that could be probably interesting in in some application. Like it's kind of a way of specifying like how much dependence between the clusters or the views you want. Yeah, I think that could be. I can see that being interesting.
Okay, any other questions? No other question. Then thanks, Iain, and thanks everybody to participating. And we'll have another seminar next Friday. So stay tuned. Okay.
Yeah, thank you guys very much.
Okay, have a nice weekend.